Hello everyone, welcome to Unoya. My name is Rizwan. I hope you all are doing well. As mentioned in the last video, here we will be discussing about real numbers. Chapter 1 of the NCERT class 10 textbook. Okay, so before coming to the real numbers, let's recall some of the families of numbers. Okay, some of the families of numbers that we have studied in the earlier classes. Okay, then we can reach the real numbers. Okay. So the first family of numbers, or the most basic family of numbers, is the natural numbers. Okay, natural numbers means counting numbers. Okay, counting numbers 1, 2, 3, 4, 5, etc. Okay, such numbers are known as natural numbers or counting numbers. The name counting numbers because these are the numbers that we are using to count things, right? If you have some objects in front of you, if you have some people in front of you, if you want to count them, you will count like 1, 2, 3, 4, 5, etc. Right? You cannot count like, or you won't count like 0, 1, 2, 3. Okay, you will start from 1 only, or you won't count like -1, -2, nothing like that. Or you cannot count like 1 by 2, 2 by 3. Okay, counting is always 1, 2, 3, 4, 5, etc. Okay, so that is counting. So such numbers are known as counting numbers or natural numbers. Okay, then after natural numbers, we have whole numbers. Okay, whole numbers. Whole numbers are the bigger family. Okay, okay, the family of whole numbers are bigger than natural numbers. Okay, it's the next bigger family. Okay, it's bigger than natural numbers because it includes all the natural numbers and it includes one extra number. That extra number is 0. Okay, so that's why whole numbers are known as that's why we can say that whole numbers are bigger than natural numbers. Okay, it includes all the natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. and one extra number. Okay, one extra number that is 0. Okay, so we can say that whole numbers has one more number. Okay, one more number than natural numbers. Okay, that extra number is known as 0. Okay, then after whole numbers we have integers. Okay, integers is the next bigger family after whole numbers. Okay, it is bigger than whole numbers because it includes all the whole numbers and also it includes some extra numbers. Okay, it includes all the whole numbers 0, 1, 2, 3, 4, etc. These are the whole numbers. Okay, 0, 1, 2, 3, 4, etc. These are the whole numbers. The integers also includes all these numbers and it includes some extra numbers also. That's why we can say that integers, the family of integers is bigger than family of whole numbers. Okay, what are those extra numbers? Let's recall. The extra numbers are negatives of the natural numbers. Okay, natural numbers we are familiar, right? We are familiar with natural numbers. The natural numbers are 1, 2, 3, 4, etc. So the negatives of the natural numbers means -1, -2, -3, -4, etc. Okay, so integers includes these numbers also. So we can say that the numbers in integers are 1, 2, 3, 4, 5, etc. Natural numbers 0, then -1, -2, -3, etc. Negatives of the natural numbers. Okay, so all these numbers are known as integers. Okay, then after integers we have next bigger family, that is rational numbers. Okay, rational numbers. Okay, so if you are continuing like this, rational numbers are bigger than integers. Okay, because it includes all the integers and it includes some extra numbers also. Okay, it includes all the integers with some extra numbers. That's why we can say that rational numbers are bigger family than integers. Okay, the peculiarity of rational numbers is that it can be represented in p by q form. Okay, p by q form. Okay, you all are familiar with that. Okay, p by q form. Okay, where p and q are integers. P and q are integers. That means one integer by another integer. Okay, such numbers are known as rational number. For example, 1 by 2. 1 is an integer, 2 is also an integer. 2 by 3. 2 is an integer, 3 is also an integer. -1 by 2. -1 is an integer, 2 is also an integer. Okay, so if you have a number in this form, one integer by another integer, generally we can say that p by q form. Okay, p is an integer, q is also an integer. Such numbers are known as rational numbers. Okay, and there is one more condition: q should not be 0. Okay, if q is equal to 0, then that is undefined. Okay, so q should not be 0. Okay, q can take any other integers except 0. Okay, such numbers are known as rational numbers. And I told you already that all integers are included in rational numbers. Why? because if you take any integer, let's take one integer 10. 10 can be written as 10 by 1. So 10 by 1, 10 is an integer, 1 is another integer. 1 integer by another integer, rational number. If you take 20, it can be represented as 20 by 1. Any number by 1 is that number only. So 20 by 1, 1 integer by another integer. 20 is integer, 1 is also an integer. Okay, so 1 integer by another integer, that is also a rational number. If you have minus 3, it can be represented as minus 3 by 1. 1 integer by another integer. Okay, so if you take any integers, you can write it like that integer by 1. So 1 integer by another integer, p by q. That means all integers are rational numbers. And we have some extra numbers also that I already told you. Okay, extra numbers. For example, we know that 3 by 4 is a rational number, but it's not an integer. It's in between 1 and 2. Sorry, it's in between 0 and 1. So it's not an integer, but that 3 by 4 is a rational number. If you want minus 1 by 10, minus 10 by 10, minus 1 by 10 is also not an integer, but it's an it's a rational number. That means rational numbers includes all the integers and it includes some extra numbers. Okay. Then after rational numbers, we have our topic of discussion in this chapter, that is real numbers. Okay, real numbers are the bigger family than rational number. Okay, it's a bigger family than rational numbers because the reason is same. It includes all the rational numbers and it includes some extra numbers. Okay, we are continuing like this. First, we began with natural numbers. Okay, then after that, whole numbers. Whole numbers are bigger than natural numbers. It includes all the natural numbers and include one extra number, 0. Then after whole numbers, we have rational numbers. Sorry, integers. Okay, integers. Because integers includes all the whole numbers and it includes some extra numbers, negatives of the natural numbers. So we can say that integers, the family of integers is greater than the family of whole numbers. Okay, then after integers, we have rational numbers. Okay, it's bigger than integers because it includes all the integers and some extra numbers. Now here also we have, after rational numbers, we have the next bigger family, that is real numbers. Okay, real numbers, because the reason is the same. It includes all the rational numbers and it includes some extra numbers. Okay, some extra numbers. That extra numbers are known as irrational numbers. Okay, we will discuss more about it in this chapter itself. Okay, yeah, so that is our topic. Okay, bigger than rational numbers, we have real numbers because it includes all the real numbers and some extra numbers. That extra numbers are known as irrational numbers. Okay, or we can say that rational numbers and irrational numbers together constitute real numbers. Or we can divide the real numbers, the entire family of real numbers, into two parts. First one rational numbers, second one irrational numbers. Okay, like that. So that is our today's topic of discussion. Okay, so let's move to your textbook. Okay. Okay, so here you can see your textbook, real numbers. Okay. Okay, so here we are beginning with the fundamental theorem of arithmetic. Okay, fundamental theorem of arithmetic. You can see the theorem here. Okay, here you can read this theorem 1.1, fundamental theorem of arithmetic. Okay, first I will read this, then I will explain. Okay, here you can read, every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Okay, that means here, according to fundamental theorem of arithmetic, we can say that every composite numbers, okay, composite numbers means numbers other than prime numbers, okay, other than 1 and a prime number, such numbers are known as composite numbers. Okay, all other natural numbers. Okay, that means the numbers having more than 2 factors. Okay, more than 2 factors, such numbers are known as composite numbers. Okay, now every such composite numbers can be factorized. Okay, I will explain it. Okay, I will explain it later. Okay, so it can be, I will explain with examples later. Okay, now here you can understand that every composite numbers can be factorized, or it can be expressed as product of primes. Okay, product of prime numbers, and this factorization is unique. It's unique. You cannot find any other way. I will explain with example, don't worry. Okay, first understand that this factorization is unique. Apart from the order in which the prime factors occur, the only thing you can do is you can change the order of them. You can write first 2, then 3, or you can write first 3, then 2. That's up to you. That order you can change, but the numbers won't change. Okay, if you have selected one composite number and if you have prime factorized it, you will always find the same prime factors, same number of times. Okay, I will explain with example. Okay, let me give you one example. Let's take a number. Which number? Yeah, let's take a number 16. Okay, a composite number 16. Okay, now here I'm going to prime factorize this 16. Okay, here I'm going to prime factorize this 16. Okay, so you should begin with 2. 2 is the smallest prime number, so let's begin with 2. Okay, 16 divided by 2. First, let's divide this 16 by 2. Okay, 16 divided by 2 is 8. Okay, 8. Okay, then again with this 8 also you can divide by 2, right? 8 is also divisible by 2. So with this 8 also you can divide by 2. Repeat the same division. 8 by 2 is 4. Okay, 8 by 2 is 4. Now this 4 also is divisible by 2. So continue with this 2. Okay, so 4 divided by 2. What is it? It is 2. Okay, now 2 is a prime number. Okay, here we have reached 2. It's a prime number. Okay, so you can stop here. So we can write this 16. Okay, we began with this 16. Okay, we can write this 16 as 16 is equal to how many 2's? 1, 2, 3, 4. Okay, 4 times 2. So that means 16 is equal to 2 into 2 into 2 into 2. Okay, this is the prime factorized form of 16. And this is unique. You cannot find any other prime factorized form for 16. Okay, this is unique. The only prime factor of 16 is 2. It is occurring 4 times. Okay, now let's take another number. Let's take 15. Okay, 15 and let's prime factorize this also. Okay, this 15 we cannot divide it by 2. 2 is you should begin with 2. It's the smallest prime number. Okay, but we cannot divide this 15 by 2, right? 15 is not divisible by 2. So let's move to the next prime number 3. Okay, next prime number 3. Okay, now divide this 15 by 3. What is 15 divided by 3? It's 5. Okay, and 5 is a prime number. Okay, so you cannot stop here. So here you have prime factors 3 and 5. That means 15 can be written as 15 is equal to 3 into 5. This is the prime factorized form of 15. Okay, in the same way, and 15 is also a composite number. 16 is also a composite number. Okay, you can prime factorize any composite numbers like this. And this prime factorized form is unique. You cannot find any other form. Okay, for example, in this 15, 3 into 5. Only 3 into 5 are the prime factors. You cannot find any other prime factors. The only thing is that you can change the order. First, you can write 3, then 5, or you can write first 5, then 3. That order you can change, but the prime factors are always same. That you cannot change. Okay, so this is simply the fundamental theorem of arithmetic. Okay. So hope the fundamental theorem of arithmetic is clear for you. Now we can use this prime factorization to find the LCM and HCF of two numbers. Okay. So for that, I can show you one example in your textbook. Yes, you can see example 2. Okay. In this example, we have to find the LCM and HCF of 6 and 20 by the prime factorization method. Okay. So for that, we have to prime factorize these numbers. Okay, you can prime factorize this 6 like this, 2 into 3, or 2 raised to 1 into 3 raised to 1. This is the prime factorized form of 6. Similarly, you have to prime factorize this 20 also, second number. If you prime factorize 20, you will get 2 into 2 into 5. You can see all these are prime numbers, 2, 5, 3, all are prime numbers. Okay, so 20 can be written as 2 into 2 into 5. 2 into 2, 4, 4 into 5, 20 only. Okay, that is 2 into 2, 2 square, 2 raised to 2, then into 5 raised to 1. Okay, so these are the prime factorized form. Okay, now you can read here, you can find the HCF of 6 and 20 equal to 2, right? That you have already studied in the early classes. Okay, because in the prime factorized form of 6, you can see 2. Okay, and in the prime factorized form of 20 also you can find 2. Okay, but in the prime factorized form of 6 you can see 3, but this 3 is not available here in the prime factorized form of 20, but so that 3 is not a common factor. Similarly, in the prime factorized form of this 20 you can see 5, but that 5 is not available in the prime factorized form of 6. Okay, so 2 is the common factor here. Okay, and 2 is the highest common factor. Okay, okay, so we can say that 2 is the highest common factor between 6 and 20. Okay, here 2 is occurring 2 times, but here it is occurring only 1 time, so you have to take only 1 2. Okay, so we can say that the HCF of 6 and 20 is 2. Okay, now with the help of the same prime factorized form, you can find the LCM of these two numbers. Okay, HCF is equal to 2. In the same way you can find LCM also. Okay, but the method is different. To find the LCM, you have to take all the prime factors. For 6, the prime factors are 2 and 3, 2 into 3. And for 20, you can see 2 into 2 into 5. So you have to take all of them together. Okay, so yes. So here from in the 6, you can see 2 raised to 1. In the 5, you can, in the prime factors form of 20, you can see 2 raised to 2. So you have to take that this 2 raised to 2 only. Okay, 2 raised to 2. This 2 raised to 2 is the highest power. So you have to take that only. Okay, if you take this, then it means that this is also included, because this is only 2 raised to 1. If this is higher power, then you have to take that. You have to take the higher power. Okay, here 2 raised to 2 is the highest power, so you can take that 2 raised to 2. Okay, then you can see 3 raised to 1 in the prime factorized form of 6. This 3 you cannot find the in the prime factorized form of 20, so you can take this 3 raised to 1, because you have to include all the prime factors. Okay, if you have 2 powers, you have to take the highest powers. Okay, if you have 1 power in the first number, for example 6, and you have another power in the second number, for example 20, you have to take the highest one only. That you can see here in the case of 2 raised to 1 and 2 raised to 2. 2 raised to 2 is higher, so we have taken that. You can see here LCM of 6 and 20. Okay, 2 raised to 2. But 3 raised to 1 is only with 6, so that is the highest power. So that's why we have taken that 3 raised to 1. And this 5, you can see the 5 raised to 1. This is also with 20, that's why we have taken that. No, you cannot see 5 here. Okay, so you will get 2 raised to 2 into 3 raised to 1 into 5 raised to 1. This is the LCM. Okay, 2 raised to 2 is 4, 3 raised to 1 is 3, into 5 raised to 1 is 5. So 4 into 3 into 5. 4 into 3 is 12, 12 into 5, 60. Okay, so we can say that LCM of these two numbers is 60. Okay, and we have another important property here. Okay, you can see for any two positive integers a and b, HCF of a comma b into LCM of a and b equal to a into b. Okay, I'm reading it again. For any two positive integers a and b, HCF of a in a and b into LCM of a and b equal to a into b. Here you can see the same situation here in this question. Here in the place of a and b, we have 6 and 20. The numbers are 6 and 20. Okay, LCM is 60. Okay, okay. So yes, yeah. The LCM between these two numbers is 60. Okay, and the HCF is equal to 2. Okay, LCM is 60, HCF is 2. What you will get if you take the product HCF into LCM, that is 60 into 2, you will get 120. Okay, 120 is the product of HCF and LCM. Now, what you will get if you take the product of the numbers, that is 6 multiplied by 20, that is also 120. Okay, so the product of HCF and LCM is equal to the product of the numbers. Okay, that's what you can see here. For any two positive integers a and b, HCF of a and a comma b into LCM of a comma b equal to a multiplied by b only. Okay, that's the same thing you can see here. For 6 and 20, HCF of 6 and 20 is 2, LCM of 6 and 20 is 60. The product is 6 into 2 into 60, that is 120. And the product of the numbers itself, that is 6 multiplied by 20, that is also 120. This will always happen for any positive integers. Okay. So these all are the topics of discussion in this video. I hope everything is clear for you. Okay, we will discuss the remaining portions in the next video. There we will discuss about irrational numbers, and we will discuss some problems also. Okay, so thanks for watching. Thank you. Take care. Bye bye.